all, welcome to the 64-bit edition of the SecurityTube Linux Assembly Expert course and certification. Now in this video, we will look at logical operations. Now, logical operations, as already probably most of you know, consists of AND, OR, XOR or NOT. Now, from our perspective, these would be bitwise operations. Now, let me actually take you to the program so that we can look at exactly what we mean. You should be able to download the program from the link below the video. Okay, so we basically have a bunch of operations. I have NOT, AND, OR or XOR. And as I mentioned, these are bitwise operations, right? Now, here is what I'm going to do. Let me just briefly show you how data is defined in this program. I have var1, which is really 0x111 and so on, and var2, which is really the value 0, right? Both of them are 8 bytes long, as you can clearly see. And using these two values and different registers, we are going to illustrate the working of the logical operations in assembly. So let's actually go ahead and assemble and link this. And then let's link this. Of course, running this would have really no effect, and that's why we are going to call our best friend GDB in TUI mode. To Intel, break, start, and then run the program, lay out the assembly, lay out the registers. Right? Fantastic. Now the very first instruction is going to move in data from this memory location. To quickly look at the data available, let's do an info variables, and let me print out both of these variables. Just like what we had seen in the source code. var1 is basically 111 16 times, and var2 is basically 0, right? So if you look at it, ending in 144 is all 1, and ending in 14C is basically the value 0. Let's just keep that in mind, though I'm sure I'll forget. Okay, so we are going to move the value inside RAX, and what is that value? Well, it's basically the value 0. So let me go ahead and do step I. So pretty much it looks like nothing happened, but the value 0 got moved inside RAX. Now bitwise NOT is going to do something very simple. Flip a 0 to 1 and flip a 1 to 0. Now because all values or all bit positions rather in RAX is 0, NOT RAX would lead to everything being flipped to all ones, and all ones is literally FFFF 16 times, because all byte positions is basically 0xFF. So let me run this instruction, and as expected we see all FFs, right? Now I'm going to move basically var1 into RBX. So let's do that. So we have a progression of 8 11s in hex. Now doing not RBX, right, would go ahead and change bit positions which are value 0 to 1 and 1 to 0, as we just said. And if you do the binary math, this really converts to all E's, right? Now after this, next instruction is illustration of the AND bitwise operation. So we go ahead and move the value 0 inside RAX, right? Let's go ahead and do that. And now we are going to move the value 8 times into RBX. There we go. And now we are going to do an AND operation of RBX and RAX. Now a logical AND is very simple. If the bit position is 1 and it gets AND with 0, then the result is 0. Only if the bit positions are both 1 does the AND result in a 1. Now in this case, because RAX is fully 0, regardless of the value of RBX, the AND operation would result in a 0 which would get stored in RBX. So let's run the operation, and as expected, RBX becomes 0. Now let's go ahead and load the value 118 times into RBX, and let's load the and after that let's do an AND operation between this value and the value picked up from the same memory location. So really all we are doing is an AND of this value with itself, right? And as one can imagine, the result would be the same value because all bit positions match, and the ones would get ANDed with the ones and the zeros get ANDed with the zeros. So after the AND operation, nothing changes. Great. Now we look at the OR operation. Now OR is very, very interesting. Apart from the case where both bit values are 0, which is 0 or 0 is nothing but 0, everything else in the OR operation, which is 1 or 1 or 1 or 0, operates and gives you the result 1, right? So let me go ahead and move the value 0 into RAX. I'm going to now move the values 118 times into RBX, which is what it already has though, but still. Now doing an OR and storing in RBX would again give us the exact same value as expected, and that's really what we get once the instruction finishes execution. Now let's load again the same value into RBX. Nothing really changes, and if we go ahead and now try to do an OR, the only variation really is at this point, rather than doing an OR register to register, we are doing register with memory location. The value would again remain the same in RBX as expected. Now let's look at the XOR operation. The XOR operation is very interesting. So if you remember, A XOR B is AB complement plus BA complement, right? Fantastic. So if I were to break it up, 1 XOR 1 is 0, 0 XOR 0 is 0, 1 XOR 0 is 1, right? So keep that in mind. And now let's proceed with this. So we move an interesting little value inside RAX, and we move another value in RBX. Now if you really closely look at these values, what you would actually find is basically that here in RAX there was actually a 0 which was there, which of course is not being shown because it doesn't make any sense. But if you align the individual bit positions, basically what we would find is that we would actually have a 1 XOR with a 0 or a 0 XOR with a 1, right? And hence the result inside RAX after this XOR operation finishes is pretty much going to be all ones, as we would expect. Now here is the next interesting one, XOR RAX with RAX. Now when you XOR a value with itself, then the 0 XOR with the 0, which becomes 0, and the 1 XOR with the 1s, which again becomes 0. So XORing a number with itself will eventually just give you a 0. Just as we expect, RAX is now 0. Fantastic. Now let's do a XOR with a memory location. the value inside RAX is 0, and the value which is there in this memory location is basically 0x11 8 times, right? Now let's run this instruction set, and what we'll do is let's look at that memory location. If I remember well, this was var 1, and if you notice, right, there is pretty much no change to the value as expected. Now after that, the last 3 instructions is really the syscall for exit, so we can continue. There you go. So hopefully in this example, not, and, or, XOR and all of that is totally clear to you. I would highly recommend running these instructions in GDB just the way that I did, so that you can have full clarity into what is happening. Hope you enjoyed this video on Pentester Academy, and if you like what you see here, I would really appreciate if you can recommend us to your friends and colleagues in the InfoSec community. Thank you very much, and see you in the next video. Bye-bye.